So hello, it's great to be here today. Thanks for the invitation, and let's start. Serverless, how to speed up tests over 300 times and achieve continuous feedback. Just a few words about me. I'm Tomasz Konieczny. I currently work for RAW, that's the New York-based digital healthcare startup, as senior key engineer, and I'm mainly responsible for test architecture and infrastructure. But in the past, I did very different things related to software development or quality in general. I also worked as a DevOps engineer. So this today's presentation will connect these two different areas. But let's start with a basic question. Why do we execute end-to-end regression tests? Or maybe why do we execute regression tests in general? Because during the development of some new functionalities, it's possible that we'll introduce bugs to already finished ones. And that's why we need this regression tests to detect these possible bugs. But why do we need high-level ones? Because these are the only ones that can guarantee that something is actually working correctly. So that's why we need them. And at the same time, there is one serious problem related to them. So they're really slow and time-consuming. That's the problem we'll try to solve today. Solution for that is automation. I mean, if we automate something that's repetitive, and regression tests definitely are, because we have to repeat them again and again during the development process, then we can save some time on distributed execution. The second thing is we can get feedback way faster with automation. So maybe instead of time, we should think more about execution speed, because it's all about speed. I mean, faster execution means faster feedback. If we'll be able to execute tests faster, then we'll get feedback faster. At every repository push, at every pull request, because we can easily verify if the functionality is working fine with automated tests. And faster feedback means faster delivery. If we'll be able to get this feedback faster, then we can actually deliver faster because we'll have the better predictability. So that's why we automate tests. We can execute them way faster, maybe even in minutes instead of even hours. And if we have some automated build process, we can get this feedback immediately after every repository push, at every pull request. So it's great, isn't it? Well, then the problem appears. I mean, we develop the application, it becomes more and more complex, and it also means that we need to write more and more tests, and basically the test set also grows. So execution time increases, 10 minutes, 30 minutes, maybe even hours. And basically, we have the same problem that we had earlier. So basically, the tests aren't fast anymore. But let's assume we have 500 Selenium tests, and execution of each of them takes about 20 seconds. It means we need almost 3 hours to execute this whole set. It's a really long time, and we just can't integrate it in any development workflow. How can we solve it at this time? Because we already have this test automated. We can think about a few, I would say, standard things. So test set redesign. For example, instead of running this whole complete test set, we can introduce some smaller sets, some reduced sets, and maybe it would be fine to execute just them. Or maybe we should think more about the pyramid. Maybe we don't need every single high-level test. Maybe we can replace some of them with mid-level or low-level ones. But what if we already have the proper test pyramid? So maybe less frequent builds. Instead of running tests at every pull request, we can run them a few times a day. Maybe it would be fine. Or the easiest option, more compute resources. So instead of running just one browser instance, maybe we can run a few of them. And for example, run 4 times tests at the same time. We'll run them almost 4 times faster, maybe about 45 minutes instead of these 3 hours. But I think these solutions are solutions at all. So my answer is just no. They're just very simple workarounds. And we have to think about something completely different here. In my opinion, the only real solution is cloud. But I mean, we need to use cloud properly. So not against some virtual machines because we just know them. We have to think about services that will really help us solve the specific problem. And in this case, our goal should be the parallel test execution, because it's the only way to really speed this test up. But not 4 or maybe even 8 instances. I mean hundreds or even thousands of them. So that should be our goal. And the easiest option to achieve it is to use serverless services, because we don't want to think about this whole infrastructure part, infrastructure scaling, infrastructure maintenance, because it can be very complex. We have our code, or just to be more specific, we want to execute them and just get the results. That's all. And I used AWS Lambda to solve this specific problem, to be able to speed this test up. And I will show you the proof of concept which I implemented. If you don't know Lambda, that's the function service at AWS Cloud, and it basically allows us to deploy code in one of the supported languages, so Python, Java, Node, and a few others, and trigger it and get the results directly. What's great about Lambda is that initial concurrency is from 500 to even 3,000 concurrent functions depending on the region, and that's what we need to do. I mean, we want to trigger a lot of different functions at the same time and just get the results. And what will be really useful to implement it is a functionality named Lambda layers, because we'll have the runtime environment for specific language. So, for example, for Python in this case, because I implemented these examples in Python. But we will also need some custom libraries, custom runtimes in general, and we want to separate them from the application or test code. So that's what Lambda layers allow us to do. They allow us to create some custom runtime environment on top of the default one. So, for example, on top of this Python 3.7 that I will use in this example. So I used Serverless framework along with AWS Lambda to implement this proof of concept I will show you now. And I already have a few production-ready implementations that I did in the current company, but I wanted to show it here in the easiest possible way to show you the general concept, the general idea how to implement it, instead of trying to show you something like very complex, very production-ready. So let's start with the Lambda layers part. Let's build our custom runtime environment. So let's create Lambda layers directory. We'll have all our dependencies related to layers there. So let's create two different directories, Chrome and Selenium. Inside the Chrome directory, let's put the binaries like Chrome browser or Chromium browser, and also Chrome driver. And let's also add the second directory, Selenium, where we will put all other Python libraries. I just script install them into this specific directory, so we'll be able to deploy them easily. There's also one more file, so Serverless YAML. That's basically the description of the infrastructure part, or Lambda layers part to be more specific. So now let's see this Serverless YAML file. We can see the service keyword here, so that's the name of our service. Let's name it Lambda Selenium layer, because it will be the Lambda layer that will deploy provider settings, so AWS, runtime Python 3.7, that's the version I used here, region Europe West, so that's the region closest to me. You can use any region here because each of them supports Lambda functions. And also layer-related settings. So we have these two directories, Selenium and Chrome, and we'll just map these directories to the specific layers. And then it was that easy about a year and a half ago when I first started to work with Lambda functions. But currently it's a bit more difficult. We have the deployment package size limits, so it's not that easy to deploy it, because we have up to 50 megs of direct sources upload, and we have up to 250 megs that we can upload with Lambda layers. And current Chrome browser versions can be a bit heavier, so it's not possible to deploy it directly. That's why I had to find some workaround. And the idea is really simple. We can compress the browser binary before the deployment, then we can deploy it in this compressed form, and then decompress it during the function runtime. Because we have the TMP directory during the function runtime that we can use it as storage. We can put up to 512 megs there. So the idea is to just decompress this browser binary during the function runtime to the specific directory. But it's really important to choose the compression algorithm wisely here, because we don't care how long it will take to compress this browser, because we'll deploy it maybe a few times a month, but it has to be really fast in terms of decompression. So there are two algorithms that are really great for this purpose. One of them is tar-xz or LZMA. The second one is Brotli. But in case of Python, it's easier to use the tar-xz because it's supported by the tar file library. So just a very simplified method, extract dependency, that will extract it from the op directory to the TMP. So we'll be able to use this browser inside the Lambda function. I skipped the error handling intentionally. I mean, all these examples will be like really simplified to show you the main concept instead of trying to implement something like really complete. Then we have to think about test runner function. So that's the function code that will be executed. So basically our tests. And in this example, we have just one file here. So that's handler py. In real life, we would have a lot of different test files here. So basically, we'll deploy every single test into the Lambda function, and we'll just trigger the specific one of them. But in this case, we have just the one file and the serverless YAML again, but this time for the function-related settings. So it will allow us to deploy the specific function. Let's start with serverless YAML again. So here we can see the service name, Lambda test runner, then provider-related settings, so AWS, again, Python 3.7 runtime, region, memory size, 1 gig of RAM should be enough here, and timeout 30 seconds. Execution of every single test takes about 20 seconds, it should be fine. And then function-related settings, so handler, that's the function that will be executed, so Lambda runner function inside handler py file, and Lambda layers that should be connected, so these two layers that were created earlier, Chrome and Selenium layer. And now let's see the handler file. So that's the test code that will be executed there. As I mentioned, in real life, we had a lot of different files, different tests. Here's just like the runner part. So we have standard Selenium imports, WebDriver, browser options, or Chrome options to be more specific, JSON, and then the Lambda runner function that will be executed. We have two different arguments here, so event and context. That's how we can pass some custom arguments to the Lambda function from the test runner. And we have this test extract dependency function that will extract the browser binary. So we'll have the Chrome browser binary available at TMP directory. Then very simple test result storage. So it will just store the state of this test, if it passed, if it failed. And we need to configure the Selenium part. So browser options, we need to set the custom binary location. So in this case, as I mentioned, it will be inside the TMP directory. Browser arguments that are like really required to be able to run the browser in this headless Lambda environment. So headless mode, disable dev SHM usage. So it basically disables the Linux shared mem. It's required to be able to run this browser there. And two next arguments are optional, so single process and no sandbox, but they allow to speed up this execution a bit. The browser works a bit faster with these custom settings. And then the driver path, it's again in the custom directory. So basically Lambda layers are copied to the up directory. So we'll have this Chrome driver there. We just have to set it here, so it will be configured as a custom one. And then the actual test code. I skipped this part because it would be just the plain Selenium. So it won't be really different. We can print anything to std out here, and it will be returned to the test runner. And then we just save this, create this response, again, 200 to make it a bit simpler. We just return this response here. The second part of this is the test runner. Again, I try to really simplify the example I will show you. In real life, it would be a bit more complex. I will show you how to extend it in later during this talk. But let's start with the imports. So Boto3 library, that's the official AWS SDK for Python, ArcParse for parsing arguments, YAML, JSON, base64 for creating requests, parsing responses, and concurrent futures because we want to trigger lambdas in different threads and wait for to get the results. Then the test set part. So in this case, I also skipped the data loading part and the test set part. So basically, we'll have the test set file, in this case, YAML, that will contain the list of the tests that should be executed. We have 500 different tests, so it will be just the list of the test cases from 1 to 500. And we'll just read it from this test set file and put it into the VM data variable. And then the data dictionary. So that's basically the execution state storage. So is the test scheduled for execution? Is it executed? If it's executed, what's the result? What's the output? And then basically I added it to every single test case ID. So for example, we can check if test case number 3 is being executed or already finished. Then the configuration of Boto3 library. Again, it's hard-coded here to make it simpler. So just access keys and secrets. Then the invoke test method or function that will actually invoke specific Lambda function. It contains just one argument, so that's test case ID. We'll pass, for example, that it should execute test case number 5. And as I mentioned, every single Lambda function will contain a code for every single test, and it will just execute the specific one of them. Then we update this execution state. So it's marked as scheduled. Then we invoke the Lambda function. So here we can see this function name that was deployed earlier. Invocation type request response. It's really important here because I wanted to make it as simple as possible. So it will just trigger the Lambda function when wait to get the results and get the results directly. So we won't need to add additional things on the infrastructure part. And payload, so here we can pass the custom arguments to the function. For example, the specific function will execute just this specific test. We can, for example, pass that it should execute this test case number 3. Then after it's finalized, we mark it as executed, then save the output and extract the results, so if it passed or if it failed. Then the threadful executor. So basically here we can execute triggered in different threads. Again, hard-coded, so hard-coded number of workers, 500, because that's the number of tests we have. And that will just invoke this invoke test method 500 times with different parameters from this async set. So test case 1, 2, 3, etc., up to 500. And it will just get the results and will get the output. I skipped the report part because it's really easy to implement, so it's not that interesting. But here is the example output. I executed just 5 test cases to make it more readable. Otherwise, if I would execute 500 of them, it will be completely unreadable. So we can see test cases from 1 to 5 marked as scheduled. Then they are marked as executed. So we can see that the order is slightly different here because, well, it's the concurrent execution. So these functions finish in slightly different times. Then report, so every single test case passed. And you can see the very basic summary. So 5 test cases passed, 0 failed. And I also used time comment. So we can see here that the total execution time was about 25 seconds. Instead of about 100 seconds that it would take normally for these 5 test cases. And we can also see user and sys values. So we can see that it was executed on the Lambda side, not locally. But I mentioned we have 500 tests and I ran just 5 of them. What would be the execution time for this whole complete test set? Well, it would be about 30 seconds. If we include the deployment times, it would be about 40 seconds. It's a really significant improvement of these execution times because we just reduced the execution time from almost 3 hours to about 30, 40 seconds. But we just run 500 instances. What will be the cost of running this at Lambda, running it this way with this concept? I calculated it, and it would be about 17 cents. So if we compare it to the cost of the development, team waiting to get the results, or this unpredictability, if we can read the application, I would say it's quite low. And the second thing is that this proof of concept is really simple to implement. I mean, it's about maybe a few hundred lines of code, so it's really simple to introduce. I mean, the production-ready solution will be a bit more complex. There are also some limitations that we'll need to handle here, but the general idea is quite easy to implement. But what will be the next step? We'll need to start with fixing one of the most significant limitations. So when we trigger with the request response mode, we trigger Lambda function in this way, we will get the results directly. And it's great because it's quite easy to implement it this way. But the downside is that in this mode, the API gateway is used. So the timeout, the max timeout for API gateway is about 30 seconds. And that means that's also the max execution time for our tests that we want to run there. So we'll need to fix this one. We'll need to switch the invocation time from request response to event. The downside is that we want to get the results directly, so we'll have to extend the infrastructure a bit. But it's not that complicated. So basically, the idea is really simple. We will trigger the Lambda function, then the function will execute the test code, and after the test code will be executed, it will post the results to the additional execution state storage. So in this case, I used DynamoDB. That's the serverless database in AWS Cloud. It's really easy to use, and it was probably the easiest database that could be used here. I also thought about using queues, but I had a few like artifacts that I wanted to keep in this database, so that's why it was easier this way. It's possible to get the difference, so what exactly changed in the database, so it's possible to just get these differences on the test runner side. And basically, after the function posts these results to the database, we can get the state and check if the test was executed, get this output, etc. So now with this change, the max execution time is about 15 minutes. So it should be fine for any like end-to-end test that we would have in the real project. But how to extend this proof of concept? Well, there are a few very different things that can be implemented here. It's really dependent on the specific project needs. But I will show you a few things that I introduced in the project that I currently work for. So I, for example, use CloudWatch for low-level logs. It was really useful for the implementation, I mean, for debugging purposes. As I mentioned, I use this DynamoDB database for the storage of build state, but I also use it for some basic artifacts. So, for example, output from test execution or some additional metadata that may be useful. Also, a S3 bucket for storing additional artifacts. So, for example, some screenshots in case of test failure, or some request logs that may be useful for debugging purposes. So there are a lot of different things that may be posted there. So it's great to store some artifacts from the test execution. It may be useful in the future. And also, runner was really heavily extended. I mean, as I mentioned, the one I showed you was simplified on purpose. It was working fine, but in a real project, I had to extend it a bit. So, for example, test scheduler was heavily extended to support some additional functionalities like subtests or some execution priorities, because we have some test dependencies that we want to keep the order, execution order in the correct way. So that's why I also implemented some test dependencies. Also concurrency limit and ramp up. So functionalities that are mainly known from performance tests that were needed here, because triggering 500 tests at the same time on some store environments, some development environments, these environments sometimes weren't able to handle that significant load. And ability to limit this concurrency in case of some slower environments, for example, from 500 to like 50 tests at the same time, will still allow us to run these tests quite fast, and at the same time, it will allow these environments to survive. Or maybe the second part, the ramp up, so ability to run the tests with lower concurrency at the beginning, and then scaling it up after some time to the target one. So basically, it allows the application environments to scale up if we have some scalable infrastructure. If environments are able to scale up, then we are just giving them time to scale up. So it's also really useful. And in the end, I will say just two more things. I mean, cloud is really powerful. I mean, it allows us to implement things that weren't possible earlier, or at least were really difficult to implement. Because using Lambda or any other function service isn't the only way to achieve this concept. I mean, I used, for example, Kubernetes in the past, and it was working fine, but I had to care about everything. I mean, infrastructure maintenance, scaling. I had to introduce some auto scalers there, and it basically became quite complex. And cloud allows us to do some things in easier way, but it's really important to use it wisely. So using services that will really help us solve specific problems instead of using services that we already know. And that's the second thing. So it's all about thinking outside of the box. I mean, I'm not some cloud expert. I'm just a QA that uses cloud from time to time. And I was still able to implement something that really significantly improved our development processes. So it's all about thinking outside of the box and thinking how we can solve some problems differently. And it would be all. Thanks. I hope you enjoyed this presentation. And if you have any questions, I can